All right.
Good. So welcome to the second speaker, Kushal. Yeah, have a screen, have a talk.
Awesome. Hi all. Wish I could be there in person, but new age. So today I'm going to talk about impurities in BECs, a setting I think that's very familiar for people at this workshop. So I will not spend too long on the motivation of these problems, but just give you context for what type of physics we've been thinking about a little bit. So the idea is we have some mobile impurity in a three-dimensional BEC, and this problem has been studied, very thoroughly. It's an old problem. There's history, especially in the last 10 years or so, a lot of good work has been done, many by people who are attending this workshop. So what do we know about this system? For finite mass impurities, when they're quite slow, we get this picture of a Bose-Polaron that is, some quasi-particle with an effective mass. You can measure it through RF spectroscopy, and a lot of good work has been done there. There's also older work, for example, by Eric Cornell and many other theory works as well, where if you examine the case of infinite mass and very fast impurities, you get Landau's kind of typical superfluidity, that if you increase the relative speed of the condensate around the defect, you end up getting these type of shock waves arising from a emission of excitations scattering off of this infinite mass defect. And this can be thought as a form of a Cherenkov effect, in the sense of you have a particle whose relative velocity is moving much faster than its environment. But in this case, because it's infinite mass, it's kind of a very classical kinematic picture. There's no real interaction scale or recoil scale necessarily between the impurity and the condensate around it. And the question we're interested in here is a natural extension, which is what happens when we have a finite mass impurity and start moving it very quickly. And of course, as we know from the Polaron side of the picture, rather than just talking about the bare impurity mass, we should also talk about the strength of the interactions between the impurity and the atoms around it, because it's really kind of the effective mass that will set a scale in the system. This could give different physics on both of these sides. On the Cherenkov side, if you have a finite mass impurity that has recoil, it may not be able to produce shock waves like this, or it may exhibit very different physics. Conversely, on the Polaron side of things, if I now take this Polaron and I start increasing its speed to be very quick, it's not clear that it forms the same type of quasi-particle that we're used to understanding, especially if you're doing it in a far from equilibrium setting. So speaking of, the two settings we'll look at here is the ground state of the system. I'm labeling it a finite momentum ground state just partly for semantics purposes, as opposed to the true ground state of the system if there is dissipation, which would be zero momentum. But these systems have translational invariance, so let's assume that the momentum is well conserved during any experiment. And this would be the case of a finite momentum Bose-Polaron, for example, if the impurity was moving sufficiently slow. We're also interested in the far from equilibrium dynamics of the system done through a Quench protocol, which is typical to these cold atom systems. Let's say we have an impurity moving at a finite velocity initially that is not interacting with its system, the condensate around it, and then through an RF pulse, for example, you can flip its internal state into one that is interacting with the kind of tunable interaction strength with its surrounding atoms, usually done through a Feshbach resonance. And this Quench protocol has also been demonstrated experimentally and is relevant. We'll find out actually that the physics we see of fast finite mass impurities in both of these cases ends up being very related. This is kind of the main result. I'll start showing you guys, and slowly unfolding over the course of the talk, is that we find a transition in a sense, it is a phase transition, but I think we should always be a little careful in this case of using that term, especially when talking about far from equilibrium. So what I'm showing here right now on the x-axis is the interaction strength between the impurity and the bosonic atom surrounding it. On the y-axis is the total momentum of the system given in units of the bare impurity mass times the condensate speed of sound. And the current plot is one of the ground state. And then I'll show you what happens with dynamics in a moment. So this is just computing the ground state energy of the system through a variational method for varying values of these parameters. And we find that there's a discontinuity in the second derivative of the energy, where it ends up for small enough momentum having a quadratic dispersion, and then switches to having a linear dispersion. There are many observables that we'll get to, which end up showing signatures of this transition, but one that is easy to see, I've written this thing called Z that's there. This is the quasi-particle residue, and it encodes how much the ground state of the impurity overlaps with the free non-interacting impurity. So how much of that bare impurity character is left in the ground state of the interacting system. And for the subsonic regime, this is actually your typical polaron picture where you have some finite quasi-particle residue. But the moment you cross the transition, if the momentum is large enough, this actually vanishes identically for all values. And it vanishes discontinuously at this transition. The transition itself, I've drawn this dotted line that's on top of the solid one. This is a prediction of just the effective mass times the speed of sound, this effective mass being taken from the curvature of the quadratic part of the dispersion in the subsonic regime. So where the transition happened actually knows about this polaronic physics in a sense. And this is why you see at stronger interactions, it actually takes larger and larger momentum well above the speed of sound to enter this kind of Cherenkov regime. We can also look at what happens in dynamics, and we find a transition there too. I'll describe in the next slide, how we're actually extracting these parameters, and you'll see some numerical discrepancy at stronger interactions, especially about where the critical momenta are. But this turns out, at least we believe, it's an artifact of kind of the variational wave function we choose and its limitations. And there are some arguments to believe that it actually should happen at exactly the same place as the ground state transition. And in fact, these two transitions are the same. So let's start looking at a few observables in both the ground state as well as this Quench protocol, and seeing them demonstrate kind of signatures of this transition. So first we can look at the quasi-particle residue I mentioned. These are curves for different interaction strengths. Each color is a different interaction strength given at the right. For example, red is weaker than green, is weaker than blue. On the x-axis is again the total momentum of the system and in units of MIC. And the y is the quasi-particle residue. And you can see that there is a discontinuity that happens once you cross some sort of critical momentum. And for stronger interactions, this happens later. We can look at an analogous quantity in the dynamical experiment, which is a Loschmann echo. And this measures essentially revivals of the interacting system compared to its initial non-interacting state. And what I'm plotting here on the x-axis is the average velocity of the impurity, which you can take to be the same as that initial total momentum. And on the y-axis is the magnitude of the Loschmann echo really at long times, so asymptotically late times. And you see that this also exhibits discontinuous transitions. And this is what we use to pick out those dynamical critical points in red I showed earlier. This is where I said you'll notice that the discontinuities on the right plot seem to happen at different momentum on the left, but there's actually some analytical arguments you can give that show that the late time Loschmann echo really should go to the quasi-particle residue, which is why we believe that while we find the transition clearly in both the dynamics as well as the ground state, the difference between the critical points is really one of numerics. We can also look at another quantity that's very natural. If you're looking at mobile impurities, and I'm telling you I'm interested in making them move fast, we should look at the velocity.
Excuse me, can I ask
Yes.
like short clarifying question?
Mhm.
So basically, in your definition of Z, basically you compare, right? So overlap between quenched and unquenched ground states. Is it correct?
Yes.
Yeah, but then we know about orthogonality catastrophe, so it should just
Yes.
be vanishing. So that is always zero in this definition, right? What do you mean?
It's not for small enough momentum. It does not. It asymptotes to a finite value.
So your momentum should be like less than 1 over system size or something.
No,
1 over c. Yeah.
not system size. Sure.
I said 1 over c. Like the impurity, it should be less than the
Right.
speed of sound. Yeah.
Oh, all right. Because normally how it works, I know for fermions,
Mhm.
and connection with Loschmidt echo. So basically your Z vanishes like some constant over system size to some power. And then your Loschmidt echo is basically same constant, but time to exactly this power. So that's, so they put, yeah. So
there is an analogy. There is an analogy here in that when you enter the regime where the velocity is fast enough that it does vanish, right? It does go to 0. It does vanish as a power law.
I see.
Similar to what you're saying. Yes.
I see. Because my analogy, of course, only about fermions. So probably for bosons, it's more benign for. Okay, great, thanks.
So we can also look at the impurity velocity, or in this case, I'm plotting in the ground state polaron velocity, I'm calling it, but this is just the derivative of the energy, the ground state energy. And by Hellman-Feynman theorem, this should also be equal to the average velocity of the impurity itself in the ground state. And you can see that for small enough momentum, it hits some finite value, and this will be renormalized by the interactions with the system, which is why you see different color curves being shifted with respect to each other. But for large enough momentum, the ground state velocity is always c. And this is the statement I made that in this subsonic regime, you can see that these velocities are linear, which means the energy is quadratic. And once you hit this Cherenkov regime, it's always linear with the same slope, which is the speed of sound. So we can also look similarly in the dynamics and find a very, very similar story playing out, again, with a slight difference in where the critical momentum happens. But with the net result that, if you're in this Cherenkov regime, the impurity always ends up at the speed of sound. And this is actually a bit interesting because I think as Misha is much more familiar with the work on 1D systems than I am, this is not the case in 1D, where not only is the impurity velocity generally a smooth function of its initial value, but it also ends up asymptoting to 0, I think, at sufficiently late times. And what happens in 2D versus a 3D situation here would be interesting to think about. So we can also look at distributions of the system rather than, for example, local observables like the velocity. And this I'm going to show distributions, momentum distributions of the ground state. So the picture to keep in mind here is if we do, for example, if we prepare the ground state of the system and then do time of flight imaging, and we look at the momentum distribution of the single impurity, you're assuming a single impurity in a homogeneous VEC. And then instead of looking at its 3-dimensional momentum distribution, you look at just the distribution of the momentum's magnitude. So you're looking at essentially kind of radial shells or spherical shells of the momentum. That's what I've plotted here. It's a little easier to see. You'd see these same signatures in the full 3D distribution, but that's harder to plot. So for impurities that are in the subsonic regime, you see kind of a sharp delta peak here. This is partly the same story I was telling you before, and that the height of this peak is just that quasi-particle residue. You can show that the distribution has to look like this. And there's some small incoherent part. But if you go to this Cherenkov regime, as I mentioned, the residue vanishes completely. You only get an incoherent distribution. And the interesting thing is that as you cross the critical momentum, the critical line, you see these two things kind of turning into each other. And that as the height of the delta peak goes down, the incoherent part becomes sharply peaked at that same impurity momentum value, and then starts broadening out again afterwards. So, at the critical line itself, critical point, regardless, it's basically all the momentum of the impurity is somewhat localized around one value. We can also look at distributions in the Quench dynamics. Here, we're going to look at real space density distributions. This would be, for example, what you measure by absorption imaging of the bosonic atoms in the condensate. And here, we're now back in this regime of these shockwave type pictures I showed you from Eric Cornell earlier. And in the subsonic regime, what you'll get, this is a density distribution of the system in just a 2D slice of it, is basically some sort of spherical wave that ends up spreading out from the impurity. That's that kind of bright dot at the center of the picture. We're in the relative frame of the impurity there. But if you go to the Cherenkov regime, you clearly see the same type of cone, and then these density ripples that come from the Bogoliubov dispersion of the excitations that are there. So I think this is kind of interesting that you still see these effects even for a finite mass impurity, given that it's sufficiently fast. And I will show you some fun animations to kind of elucidate this. So let's start in the top left. What happens if you're having weak interactions and you're in the subsonic regime? This is that spherically expanding wave I mentioned. And you can see that the interactions kind of generate this wave, and it just spreads out and then eventually washes out in the system. And just for reference, let's keep that there. Then you can also look at what happens for weak interactions that are supersonic. And this is that Cherenkov cone I mentioned. And you can actually see, let me rewind a little bit. You can see that the cone angle changes. This is something that is very much only due to the finite mass of the impurity, because it's recoiling, the impurity itself is slowing down. And it's that relative, if you're familiar with the usual, infinite mass effect or Cherenkov effect, that the cone angle is set by the relative velocity of the impurity and the speed of sound around it. But as it slows down, the angle of the cone gets shallower, but you still see a persistent cone at late times, and also these ripples in front of the impurity, which I think is not there in the classic, which is only there due to the superfluid nature of the condensate. We can also look at what happens for strong interactions, and here the case is a little bit interesting. So both of the bottom plots will be started supersonic. So with the impurity being above its bare mass times the speed of sound in the medium. But we can look at what happens if you're below that transition, this interaction, renormalized transition. And you see something very similar to the subsonic case, which is this sort of spherical wave that propagates outwards. And at late times, there doesn't seem to be any persistent shockwave in front of the impurity. And this matches the fact that the impurity's average velocity itself falls below the speed of sound in this case. But if you're sufficiently far above the transit, if you're sufficiently supersonic so that you're above this transition, you'll see something slightly different, which at short times looks similar. But then as you get to later and later times, this shallow shockwave in front of it seems to persist. And this corresponds basically to the average velocity of impurity still ending up at the speed of sound at late times and not falling below it. This thing I showed you.
Sorry. Can I ask a question about, actually even two questions. The first one is about this Fronten supersonic regime. First of all, it doesn't look quite conical, right?
Yeah.
It's like more parabolic, no?
And I think there's a paper, I think a couple of good work studying this by Jacopo Corsuto. I think that the particular shape of it, rather than it being a cone, may be related to the nature of the dispersion relation.
Yeah, and furthermore, there is a sharp difference with respect to what we know about Cherenkov radiation from textbooks, is that there are ripples ahead of the impurity, right? Although the impurity moves supersonic, somehow it manages to produce ripples ahead of it. So it's like, you know, superluminal, supersonic propagation of perturbation. This looks strange, right?
Yeah, it's a bit interesting, but you actually see this in the actual experiments, even with the infinite mass defect, I think. That you see, you know, some ripples and of the condensate in front of it.
So it's counterintuitive. So intuitively, one would expect that there are just no excitations which propagate faster than sound speed. Right? Yeah.
It's, I think, one of the reasons it's quite interesting.
Yeah, and another question actually, what is shown here precisely? So what is your protocol? You inject the impurity and just let it go, or you drag it with some force?
You just let it go. This is exactly the Quench protocol I mentioned, where you assume you have a single impurity. It's in a homogeneous species, so maybe a very large box trap, this type of thing. And it has some velocity. You know what the velocity is, and then you turn interactions on instantaneously and you let it go.
Then it should decelerate, right? And
it is. So these plots are done in the frame moving with the impurity, the average velocity with impurity. It's in this Lilo-Pines frame, if you've heard of it.
I see. Then this might be the reason why there are these ripples and ahead of the impurity. Just at late times, it doesn't move with supersonic velocity.
Yes. You should actually think about these pictures as slowing down, right? Because we are always in the impurities frame in this, but the impurities frame itself is slowing down.
Yeah, I see. Thank you very much. Thanks.
So the plots I showed you for these transitions were for equal mass ratios between the impurity and the atoms around it, but the same thing, all the same story holds true for different mass ratios. So what I'm plotting here is the dynamical curves extracted from this Low-Schmidt-Echo discontinuity, because that gives the clear signal of the transition for different mass ratios, green being 1/2, red is the same one I showed you before of equal masses, and blue being heavier. And you see what you kind of expect, which is that as you go to heavier and heavier masses, the critical momentum falls back towards the classical Landau superfluidity value of just crossing the bare mass times the speed of sound. And this is where you would recover this initial picture I showed you, which is dragging a condensate fast and infinite mass defect. And there you also see these kind of ripples, for example, right in front of it. There's a few other plots that I think are clearer if you move the impurity more quickly. But this is why we call it a quantum Cherenkov transition, because you really see the critical point of this transition depending on interactions and entanglement between the impurity and the condensate around it. And it shows up in all sorts of observables, as well as these shock waves which still exist. And so we can think about, what are a few of the still unanswered questions related to this. One is that at very strong interactions, aside from the discrepancy between the dynamical values in the ground state critical points, it seems that there is actually a difference between the critical momentum and just this mass renormalization. And why exactly that is happening, or being able to predict where that happens, I think would be interesting. Then, of course, there is this kind of glaring numerical discrepancy that right now we think we know why it's there, but we should check that if you use better wave functions or different methods, that you should see this coincide with what we expect. The next thing I haven't listed here, but I think it would be interesting to examine the same system in 2D. As I mentioned, in 1D, you don't see the same physical story. And 3D is quite different. So what happens in 2D, how this relates to the nature of what collisions are important between the impurity and the atoms around it are all questions I think that would be interesting to examine. And with that, I'd like to thank collaborators on this work and open up for any other questions.
I have a question about the emission of rotons. We know that a subsonic object can still emit a certain class of quasi-particles in a three-dimensional superfluid, which are rotons. So why don't you see that effect here?
That I don't have a great answer to at the moment. We don't see, I don't know if this is an artifact of the treatment or not, but typically we don't see rotons at all, even in any of the works that have been studied the subsonic regime. That would be interesting to see how they could change the story.
Is that because you just don't see the rotons in the spectrum of your superfluid?
Yeah.
In the first place. And why is that?
Right now, we're just using kind of the typical, Bogdubov treatment of it, but you don't see this roton minimum, I think, there.
I see.
Yeah.
Right. Okay. Thank you.
Hi, can you hear me?
Yep.
Yeah. So here all the results are for like attractive case, right? For the impurity and
yes.
okay.
I should have mentioned that. Sorry. It's for an attractive.
And do you have any I don't know ideas for the repulsive side? What's happening?
Yeah. So there are some results there. Not this full story of the transition and everything. You still see, I think, some decay. For example, in the Loschmann echo, this has been looked at, but you get oscillations due to existing bound states on the repulsive side. There's also interesting, a bit of an interesting story of a slightly different situation, which is rather than letting a single impurity go in a homogeneous BEC, what happens if you make the BEC undergo dipole oscillations? Then you will, I think, end up seeing the impurity, if you end up getting kicked by the oscillations around it and moving very fast. And it eventually, if the interactions are strong enough, will end up locking onto the BEC. This is also turns out to be due to this same kind of emission of excitations. And there you see it both, at least there I can confidently say, we see it both on the attractive and repulsive sides. So there is, I would expect, some part of this story to carry over, but I don't know in detail at the moment.
All right, thanks.
More questions from online people?
Yeah, another quick question. Do you have the so you can inject an impurity in your sort of thought experiment in a supersonic regime, and what you find is that it always seems to relax to the speed of sound, essentially, in your system.
Yep.
Which is a bit surprising, because from kinetic theory, if I try to apply kinetic theory into this situation, I would expect that a supersonic impurity emits some number of bosons, right? So some number of sound waves or sound wave quanta, and relaxes through such an elementary process. It could be an elementary process in principle. It relaxes to a momentum which is such that its velocity is below the critical velocity or equal to the critical velocity. So there should, in principle, be a finite density, the probability density for a particle to have a velocity, a speed, which is below the critical. So on average, from purely kinetic considerations, I would expect that an impurity, well, in its steady state, has an average velocity less than the critical velocity, not exactly equal to the critical velocity.
Yeah, it's a very interesting question. It's also one that bothered us a little bit, and we thought about a fair amount. What I can say is that there is always, of course, some finite probability, as you mentioned, for the impurity to be below the speed of sound. I think you can even see that in these distributions I showed, right? The critical value, this thing ranges all the way to zero, even in the supersonic regime. I think one argument to make can be that, let me try to see if I can show you something a bit different. So these are plots. It's a little bit complicated to parse, but of the impurities average velocity coupled with the phase space for excitations from this kind of like kinetic theory or Fermi's golden rule type treatment that you were mentioning, at short times where it should and weak interactions where it should be valid. And it turns out that the phase space, at least for sufficiently weakly interacting impurities, even if you start them supersonic, their phase space to have these excitations decreases as you approach the speed of sound because of the form of the dispersion, the Bogusław dispersion. And maybe this is why they get stuck there. At least one argument. For very strongly interacting impurities, yeah, you can't use the same argument, but and you do see a sharp drop in average velocity initially, but it seems to still saturate to see it long times. But if people have better treatments of it to check, I think this would be interesting to see.
Yeah, this is curious. This
is
certainly counterintuitive. Right, thank you.
Yep.
More questions? Okay, I will count from 3 to 1, then I will stop recording. 3, 2, 1.